I'm Marcello Laurenti. I'm a second-year PhD student from University of Rome La Sapienza, and today I'm going to show you some preliminary results about optimization and modeling of SLA printed lattice structure mechanical properties. So let's dive in. But first, a little bit of a background. As you well know, additive manufacturing involves an iteration cycle that starts with the design of your desired part. It follows with the actual manufacture of your part once you have chosen your first guess of print parameters. And when you have gathered enough specimen, you can start your testing campaign. And after gathering enough data, you can build a weak model, and together with some practical consideration, you can modify your design, you can modify your print parameters, and you continue this cycle until you reach your desired mechanical properties. But especially for SLA printing, mechanical properties are highly susceptible to small changes in print parameters, since micro defects can happen, such as microvoids and under-polymerization inside the piece, and that can hugely impact the static but also the dynamic behavior of your piece. So this study will focus mainly on lattice structure. Why? Because they are a hot topic nowadays, since they are lightweight and porous structure. They are used in different fields, such as, for example, the space field. For example, here it's a quad thruster block that improves fuel efficiency in space rockets, but also is used mainly in biomedical application, such as, for example, bone replacement, since with using lattice structure, you can tailor better mechanical properties of your part, and in doing so, your patient will have enhanced comfort, and there will be less impact on the health of the surrounding bones. So this is the methodology overview of this study. It started with the experimental design. So the design has been conducted with an topology, the 3D printing process, and the compression testing, and follows the deep learning modeling and a shop analysis to understand the process dynamics, and it ends with a genetic optimization of the aforementioned mechanical properties. So at first, let's dive in the experimental design. In this study, we have considered truths like lattice structure, and we have considered 5 main cell types: the body center cubic, the face center cubic, the diamond, the floret, and the octet structure. In the future, that will be extended, but up to, for now, we have considered only those cells. The cell size have been varied into those 3 intervals, so 2.43 millimeters, 4.86 and 9.71. And we have varied the printing layer thickness from 10 microns up to 100, so covering the whole range of our SLA printer. We have tested the specimen in both in a parallel plane regarding the print condition, and in an orthogonal way to capture the anisotropy inside the lattice structure itself. By doing this experimental campaign, we have gathered 136 data. So, as the compression test, we have performed it using a strain rate of 5 millimeters seconds until reaching 20 millimeters of final deformation. And upon printing, we had to do appropriate cleanup, since we are using vat infusion. So, since we are dealing with a lattice structure, they are very porous and they act as a sponge. So we have to separate the excess resin by using centrifuge apparatus. So those are the mechanical results of the compression, and we can notice normal behavior of those lattice. So we have some bending dominating behavior, for example, in BCC, and some mixed behavior for floret and octet cells, but they are normal, and that's a good indicator that the print process was good. and there are no anomaly detected. So that's for the experimental design. Let's dive in the hot topic of this presentation, that is the deep learning modelization used on top of it. So since here we are trying to model multiple mechanical properties at the same time, we have used an hand-head statistical boosting neural networks. Hand-head, since in our modelization, each head will model one mechanical property at a time. It is statistical, this neural network, since we are dealing with additive manufacturing, and additive manufacturing is a partially observed environment, so it's statistical per nature. So we cannot have a modelization that gives you a deterministic output, but it needs to be statistical to fully capture the mechanical behavior of the specimen. And it's boosting since we have an model, each one modeling the error of the previous one. So we have an increased accuracy by doing so. We also have used a common backbone to homogenize the output to avoid some numerical instabilities that could occur. And we have used an encoder to compress data and to ease the computational load and to increase also accuracy. All this process and all the hyperparameters have been tuned using Bayesian algorithm. So this is the fully optimized neural network. About more in detail about the neural networks, for the encoder, we've used the anode encoder, trained at first in an anode regression task, and after training we only retrieve the encoder to project the input data into a meaningful latent space. The main block of our neural network is a simple multi-layer perception. It's very simple, but despite its simplicity, it's very great for regression. And since this is a multi-dimensional regression, it holds. And this architecture is very customizable. And in this case, we have used a bio-inspired human brain structure inside the depth of the neural network. So we have created some expansion and compression regions that created different latent space, and that eased the computational loads and allowed for the creation of sub-latent space, and that increased the overall accuracy. So as for training, at first it was trained the variational encoder, it was tuned its hyperparameters, and secondly it was trained and the hyperparameters were tuned, the backbone and all the heads. After this training process, the best performing model was retrieved, and it was used for validation on unseen data. And those are the prediction or unseen data, for example, on young models, the ultimate tensile strength, and energy absorption up to the lattice collapse. And as you can see here, the accuracy is good. As metrics, we have the continuous ranked probability score is a surrogate for the mean absolute error, but for statistical distribution. It collapses to the mean absolute error when we have a delta of direct distribution, but it's very similar. So we have an error of 1.8 megapascal for young and 1.1 megapascal for ultimate tensile strength. And that's pretty good because they're very, very low errors. And this neural network also, it doesn't look in the presentation because the colors are not right right now, but the confidence bands correctly predict the inner stochasticity of this process. So we have always prediction inside the confidence bands. Okay. So this is just for demonstration because this neural network wasn't born to do this, but if we try to reconstruct with points the shape of the curve, the reconstruction is good. But this is just for demonstration. This neural network wasn't born to do this. We have another work that do this. If you're interested, you can look it up. But this is just to demonstrate that this neural network is predicting very good our currently task. So let's dive into the SHAP analysis. SHAP analysis, if you're not familiar with, it's a statistical, it's a numerical methods that allows you to investigate how the inputs influence the output. So here we can understand somehow how the process parameters influence the output. Here, for example, we have rightfully the influence of the octet structure and the fluid structure on the final energy absorption, because those are mixed mode kind of lattice, but there are also there is some bending behavior inside of them. So of course they absorb energy. But we have also some influence on the cell scale of the lattice. So when the cell is smaller, it seems to increase the energy absorption. But looking at the scatter of the distribution, we see that it's increasing for a small value of cell size and for small value of a resolution. And that's an indicator of the effect inducing parameters. So those two, even if they are increasing the energy, they are increasing also the defects inside the specimen. So we have some conflicting behavior inside our dominium, and we can investigate those behavior by doing an analysis on the interaction of the parameters. You can do a lot of analysis, and there's no time into a 15 minutes presentation, but I'll show you just one interaction between the cell scale and the octet structure. As you can see here, we have a positive interaction between those two parameters, and that what does that mean? Octet structure is very dense, is very packed, and this interaction appear only for a small cell scale. So that means that due to the geometrical effects, there is not an homogeneous polymerization in the lattice structure, and that's causing the appearance of defects inside of the part. But since there is a lack of polymerization essentially inside of the specimen, we are creating some buckling initiation points, and that helps increasing the overall energy absorption of the lattice structure. So that's for the deep learning modelization. Now let's dive into the last part, the optimization of those parameters. So to optimize the parameters, I've used a genetic algorithm. If you're not familiar with it, it's not big science. It's just a clever way to optimize virtually any dominium. You have just to encode it into a genome and let it evolve using natural way of reproduction and mutation and crossover. So in this case, we have encoded the print parameters into a genome, so assigning each parameters gene, after gathering enough gene chromosome, and after gathering enough chromosome, we have created a genome. We have initialized the population of any individuals, each individuals with a unique randomly initialized genome, and we let the population evolve for M generation. And at each generation, it was evaluated the fitness of each individuals, and the fitness was calculated by the distance between the target prediction, the target properties that we want to have, and the actual predicted properties that was predicting the model. And after enough generation, we had an optimized solution. We have used a non-sorting genetic algorithm, the third version of it, to navigate this environment, since this is a multi-objective optimization. So let's just explore one very small case study, because, for example, if we want to optimize a structure for a production of a protection element, for example, an helmet, we want to minimize the difference from the ultimate tensile strength and the strength of the lateral collapse, because a huge difference between these two values will cause an increase in experience G-force, and that could hurt the people using this protection. So we want to minimize this quantity. We want also to maximize the energy absorption, and we want to minimize the density of the lattice to allow a cheaper manufacturing process. So if we let the population evolve, we see those results. For example, here there is a linear correlation between stress UTS and the stress of lateral collapse, and that's good because we want this. And it's the line. If we see also the correlation between ultimate tensile strength and energy absorbed, we see an almost linear correlation, but it's interesting looking at the relative delta stress and the energy absorption, because here we can trace the Pareto optimality frontier. We can choose our optimal points, our it's just they're just chosen by the user, and we can then choose the best print parameters for this case, for both vertical loading and the orthogonal loading. And those are the best parameters, and this is the energy absorption with its confidence interval. So that's all. That's this work. So that it has seen the testing on 139 lattice structure. It has seen the developing of an handhead statistical boosting neural networks, and in the end, it has been applied a genetic algorithm on top of the modelization to optimize the mechanical properties of those lattice structure. So, as future works, we plan to extend the genetic algorithm capabilities to optimize each head of the neural networks to have a better tailored neural networks on this task. So essentially, we want to increase the accuracy. We want to extend the modeling capabilities to the whole mechanical behavior of the material. That's something that we have already done in metals, but we want to use a physical informed neural network in a cooperative framework where the recurrent neural network used in this work will be used to model the mechanical behavior, but this network will be used for the integration point and the derivative point of the physical informed neural network. And of course, we want to extend the modeling capabilities also on metals and mainly on additive manufactured SLM lattice structure. So thanks, and if you have any question, just ask me.